Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota. I'm John Paul Martin, your warning coordination meteorologist. In this segment, we'll talk about thunderstorms and their structure. Here's a picture of a thunderstorm that's very intense. Here's the anvil of the thunderstorm. That marks the top of the weather-producing atmosphere for the day. Here we see the overshooting top. The updraft in this thunderstorm is so strong that it broke through the anvil and it's overshooting the top of the storm. You'll never see an anvil on a thunderstorm when it's right overhead. This is a feature you might look for when the thunderstorm is 50 or even 75 miles away. If that thunderstorm's moving toward you, it would be an indication that severe weather is possible, that's a very strong storm, and you need to keep an eye on it. Here's a schematic of a supercell thunderstorm, and on the lower right side, a radar image of a supercell. On the front side of the storm, as it's moving to the top right of the screen, moving to the northeast, the front of the storm, the forward side, is sinking air. This is called the forward flank downdraft. That's where the rain and hail is falling out of the storm. Towards the back of the storm is the updraft area. That's where the air is flowing into the storm and up. There's very little, if any, precipitation that falls through the updraft, although you can get very large hail falling there. Most of the precipitation rises through the updraft and falls out here where the air is sinking on the front side of the storm with the downdraft. Way to the back of the storm is the rear flank downdraft. This is sinking air way on the back side of the storm, and this grabs the circulation out of the thunderstorm and brings it down to the ground as a tornado. On the radar image, this is the base reflectivity image. The radar sent energy out, and the energy came back. Small raindrops return a little bit of energy to the radar, and the radar paints those blue and green. Large wet hailstones return a lot of energy to the radar, and the radar paints those on the high end of the scale, the dark reds, purples, and whites. Again, a supercell storm in a drawing and on Doppler weather radar from the National Weather Service at Bismarck. This storm is moving through Grant County, North Dakota. Supercell thunderstorms are differentiated from other thunderstorms in that the updraft in the supercell is actually rotating. It's spinning as it moves up through the thunderstorm. Supercells are highly organized, extremely strong updrafts, and again, that updraft is rotating. With supercells, there's a very high risk of severe weather, not only large hail and high wind, but flash flooding and tornadoes. In this drawing of the supercell, as it's moving off to the right, that's the downdraft air, the sinking air. You might see a shelf cloud at the leading edge of the storm. That's the wedge-shaped cloud that marks the interface between the warm air flowing in and the cool, moist air flowing out. At the interface of the warm and cool air is this wedge-shaped cloud called a shelf cloud. The shelf cloud will race out ahead of the thunderstorm. In that area, under the downdraft, is the rain and hail. Your visibility in the rain and hail will be very low. It'll be dark all the way to the ground here because of the precipitation falling out. That's reducing your visibility. Here's the updraft of the storm where the air is rising up into the storm. Again, very little, if any, precipitation falling out here as the rain and hail is pushing up into the storm and falling out with the downdraft. Monster hail can fall through the updraft and reach the surface of the ground. Here's the rain-free base of the storm where there's, again, very little, if any, precipitation, so we say rain-free, and it's the base of the storm, the bottom of the storm. Here's a picture of what the updraft might look like. Here's the clouds pushing up into the storm, that's the updraft, and you can see daylight through the bottom of the storm under the updraft, again because there's very little, if any, precipitation falling there. If the picture extended off to the right, you would see it would be dark all the way to the ground here because of the rain and hail. Here's the anvil of the storm and our overshooting top. Sometimes with a supercell, part of the rain-free base drops down to form the wall cloud. Sometimes a wall cloud will start rotating, and sometimes out of a wall cloud that's rotating, you'll get a funnel cloud or a tornado. Just because you get a wall cloud, it does not mean you'll get a tornado. What's happening here is the rain-cooled air is coming out of the thunderstorm and being sucked back into the storm right here. That makes an extension of this rain-free base, a lowering of the rain-free base into the wall cloud. Again, the wall cloud marks where the air is flowing in and up into the thunderstorm. Wall cloud, in and up. Shelf cloud, down and out. The rotating part of the updraft within a supercell storm is called the mesocyclone. Mesocyclones are often the parent circulation to tornadoes. Wind shear is a very important part of getting a thunderstorm to rotate. In meteorology, we talk about two types of shear. Shear just means a change with height, a change as you go up through the atmosphere. There's speed shear, where the wind speed is changing as you go up through the atmosphere, and there's direction shear, where the direction of the wind is changing. To get a supercell, we need both speed and direction shear in a storm. And again, the word shear just means a change with height. Why does a supercell updraft rotate? Well, the wind shear, especially in the form of the direction shear, we have wind speeds and directions changing as we go up through the storm, so we get what's called horizontal rolls forming. That's wind moving parallel to the ground and moving in a horizontal fashion, again because of the difference in wind direction as you go up through the atmosphere. These horizontal rolls run into the thunderstorm, and the thunderstorm has the updraft and the downdraft. So the horizontal roll is pulled up into the thunderstorm by the updraft, and it's pulled down to the ground by the downdraft. If the circulation reaches the ground, that's a tornado. Lines of thunderstorms form shelf clouds, along with the supercell storm also forms shelf clouds. The shelf cloud is the gust front area, marking where the warm, moist air is flowing in and the cool, moist air is flowing out. The interface is the wedge-shaped cloud that we call the gust front or shelf cloud. When you see a shelf cloud, it means, as it's moving toward you, that you're going to have a change in the wind direction and a sudden increase in wind speed. Again, the shelf cloud is where the motion is down and out. It'll move out ahead of the thunderstorm. Here's a picture of a shelf cloud with some false funnels. These are fingers of clouds sticking down. People often mistake these for funnel clouds or tornadoes, but they are not spinning. The finger is not spinning, so it is not a funnel cloud. It is not a tornado. Again, these features are often seen on a shelf cloud. Here's our mesocyclone with our wall cloud. Again, what's happening here is where you see the bright sky, the daylight through the bottom of the storm, that's all upward motion into the storm. Over here, you can see the rain coming out of the storm down to the ground. The rain-cooled air is coming out of the thunderstorm and being sucked back into the thunderstorm right here, forming the wall cloud. Again, that lowering of the rain-free base. The lowering of the rain-free base into the wall cloud. The wall cloud will point toward the downdraft. Here the wall cloud is pointing toward the rain falling out here with the downdraft. Here's a drawing, a picture, and then some arrows put over it to show you the role of the rear flank downdraft. This sinking air way on the back of the storm causes clouds, the sinking air causes the clouds to dissipate. That's our rear flank downdraft grabbing the circulation out of the thunderstorm and bringing it down to the ground as a tornado. Do you need a supercell thunderstorm to get a tornado? Well, the answer to that is no, you don't. Tornadoes can form in any part of a thunderstorm, and in any thunderstorm you do not need a supercell to get one. Very weak tornadoes that are surface-based in their circulation are called landspouts. Landspout is a common name for a non-supercell tornado. Again, they're shallow and surface-based. Here's a picture of a landspout tornado from central North Dakota. How do landspout tornadoes form? Well, we have cool air, in this case, moving south and warm air moving north. A boundary sets up between the warm and cool air, and circulations form along that boundary. Again, as the cool air pushes south and the warm air pushes north. A shower or thunderstorm moves over these boundaries, and that shower or thunderstorm has an updraft and a downdraft. So the circulation from the ground is pulled up into the shower or the thunderstorm, and that circulation can form a funnel cloud or a tornado. Again, we call these landespout tornadoes. Typically, they're very weak, do very little damage, and are not on the ground very long. You may have heard of a microburst or a downburst wind. Dry air mixes with the rain falling through a thunderstorm, and it causes cooling through evaporation. When water evaporates, it causes the temperature to cool, to go down. This cool air sinks, and the cooler the air is, the stronger the sinking and the stronger the wind. Hail that's melting as it falls out of a thunderstorm adds to this cooling, further accelerating this downward motion toward the ground. These downbursts can be wet or dry. If there's a lot of rain with it, we call it a wet microburst, and if not, we call it a dry microburst. Microburst winds are over a very small area. All microbursts are downburst winds, but again, a microburst is over a small area, whereas downburst winds is any air flowing out of the thunderstorm and down to the ground with high acceleration, with high speed. I want to talk to you a little about tornado lookalikes. We have a lot of things that look like tornadoes but aren't. We showed you some out of the shelf cloud, some of those fingers that stick out of the shelf cloud, and folks mistake those for funnel clouds or tornadoes. But in reality, those fingers are not spinning, so they're not funnel clouds, they're not tornadoes. One of the biggest challenges for weather spotters is determining if that really is a tornado I'm looking at. Two features with a tornado would be a debris cloud near the ground and organized rotation about a vertical axis. The rotating tornadic condensation cloud edges will be fairly smooth with a tornado. Many look-alike tornadoes, or things that look like tornadoes, I should say, have a more ragged or jagged look to them. You may have heard of a scud cloud. The atmosphere is moist here, and any upward motion is causing condensation. It's causing clouds to form. These cloud shreds underneath a thunderstorm are often pulled up into the storm, and they're mistaken for tornadoes. Again, look-alikes, but not the real thing. In this case, we have some fingers of clouds sticking down, but the fingers are not rotating, and so they are not funnel clouds. Again, a finger of a cloud sticking down is not much concern unless it is spinning, unless it's rotating. These fingers are actually coming out of this shelf cloud. Here's another picture of a shelf cloud with these false funnels. Again, we need to watch the finger sticking out of the thunderstorm and make sure that if we're going to call it a funnel cloud or a tornado, that it's rotating. It's got to be spinning. Here's more false funnels. In the picture to the left, this is actually a fire burning, and the smoke is rising off the fire and into the thunderstorm. So this is smoke, not a tornado. Same thing here in the top right. That's a fire burning, and this is the smoke rising into the atmosphere. No circulation there, no tornado. And in the bottom right photo, again the same thing. A fire is producing smoke, The smoke is rising into the thunderstorm. Sure looks like a tornado, but there was no rotation, and so it was not a tornado, and indeed it was a fire producing smoke that was rising into the storm. Another thing mistaken for a tornado is a rain shaft. In this picture, it is not raining here, it is raining here. That's just rain falling out of the cloud. Again, is it spinning? The answer is no. In the picture on the top right, again, it is not raining here in the picture, it is raining here. Sure looks like a tornado, but there's no rotation. It's not a tornado. It's one of those look-alikes. And finally, in the third picture, the same thing. This is just rain falling out of the cloud. There's no rotation, so we're looking at a rain shaft and not a tornado. We need to be very careful when reporting tornadoes that we're sure that there is circulation, there is rotation. The National Weather Service Skywarn website is available off of our main page. The National Weather Service webpage out of Bismarck is weather.gov/BIS, or you can spell Bismarck out. If you follow that URL with the word Skywarn, you'll get to our Skywarn training page, and we have a lot of information available to you there, including the Weather Spotters Field Guide. We also have some hail charts and wind charts there, and a lot of safety material. I want to thank you so much for watching this segment, and I urge you and your family to stay weather ready.